Welcome to the next screencast of trees. We're going to be specifically talking about how we can use binary trees to help us implement a heap and a priority queue. So, what is a heap? Heaps are basically a complete binary tree whose root value is the smallest value in the tree. So you can see a heap here where we have a complete binary tree. We have all the height minus 1 rows are full, and everything is shifted to the left as you insert into the tree. And every subtree of the tree is a heap itself. So again, the left subtree, 18 is smaller, right subtree, 29 is the smallest value in there, etc., etc. So how do we insert items into a heap? Well, the first step is to put the new item at the bottom of the heap and still keep it a complete binary tree. So we inserted the 8 at the bottom of the tree. Then while the new item isn't the root, it's moved all the way up to the top, and it's smaller than a parent, we swap them. So in this case, 8 is smaller than 66, so we swap them. And then we just keep going. So is 8 smaller than 29? Yes, we swap it. Is 8 smaller than 6? No, we're done with our insertion and we have restored the heap to being a heap. So the root node is smallest of all its subtrees, and each subtree is still a heap. So how do we remove an item from a heap? Well, we only remove at the root. That's how we get the smallest or largest. You can have a min heap or a max heap. We've got examples of showing min heaps, so it's the smallest on the top. So how do you remove it? You take a look at the root, you remember what the root is, and you're going to remove the root. So and then the actual algorithm is to replace the root with the last item in the heap. And the last item in the heap is the 66 at the bottom. So we replace the 6 with the 66, removing it from the heap. And then now, while the last item in the heap has children and it's larger than either child, swap the item with its smaller child. So 66 is larger than 18 and 8, but we're going to swap it with the smallest child, so we swap it with the 8. 66 is larger than 39 and 29, but we swap it with the 29. And now it has no children, so the heap has been restored, and we still have a heap because the right subtree is still a heap. 29 is less than anything below it, and the rest of the heap has not changed. So that's how we remove an item from a heap. We take the last item in the heap, put it at the root, and then move it down the heap based upon if it's larger than its children. Fairly simple to think about. The implementation is slightly trickier. And so let's sort of talk about using an array list or an array to hold the items, and how we can implement a heap using an array or array list. So we have the array on the left shows the heap. It's got 8, 18, 29, so it's got all the items. There are 12 nodes. So we have define the concept of a parent, node P, and a child. So the left child can be calculated as 2 times the parent's index plus 1. The right child is 2 times the parent's index plus 2. So you can, from any node in the array, you can find its children quite easily by multiplying by 2 and adding 1 for left, multiply by 2, adding 2 for right. Then vice versa, you can figure out its parent by just subtracting 1 from the child's index and then doing integer division by 2. So the example here is we're at 6, our parent is 6 minus 1, which is 5, div 2, which is 2 in integer math. So the parent of 66 is 29. You can see in the tree representation, it's easy to see. In the array, you just have to do a little math to find out who the parents are. So how do we insert using an array? Well, what was the first step in insertion? We add it to the end. So what is the end of this array? It's actually the 13th item, because that's the end. So now we say, check to see whether or not 10's parent is larger than 10. So we calculate the child to be 13. We find out who the parent is. We can do the math to see whether 10 and 66 are, or 10's less than 66. If it is, swap them. And now we need to recalculate the parent or the child variable. We set the child to the parent because that's where we are now. We're at 6. Calculate the parent again. It's 10 less than 29. We swap them. The child is now the parent, which will be 2. The parent is going to be 1 div 2, which will be 0. Is 10 less than 8? No. We're done. We have reheaped the heap, and we have a correct and valid heap in our array. So we have an array representing our heap. So how do we remove an item? We remember the root, which is the thing at 0, so we remember the 8, and then we remove the last one and put its value into the root. So we now have an array of size 12, or an array of size 12, and we've swapped the 8 with the 66, and so now we need to calculate. We have to say, set the parent to 0, because that's what the item that we need to heap down or push down the tree until it's in its right place. Calculate the left and right child, and then we calculate the minimum of the left and right child, since 66 is greater than 18 and 10. Oh, we have a breakout. If the left child is greater than a size, that means we've gotten all the way down to the bottom of the heap, and we're considering children that are nulls, basically, in the tree representation. But that's not true. So we check the min child. We look at 18 and 10, and the min child is 2, because 10 is smaller than 18. Now, is 66 greater than 10? Yes, so we swap them. And now we need to update the parent's index, set it to the min child's index 2, recalculate. If we didn't swap, we would have broken, but we're still in here. So we recalculate our left and right children, and is 66 greater than 39 and 29? The answer is yes. So now we calculate the min child, which will be the 6, 29. We swap. We update the parent. We check to see, we did the swap so we don't break. We check the children. Left is now 13, right is 14, but our array is only size 13, but it's greater than equal to the size. So we're done, because 66 does not have any children. And so we have restored the heap is now a correct heap again. And so we break out a loop, and we are done. So what are the performance of a heap? Removal traces from the root to the leaf, potentially. The last item in the heap starts at the root and then swaps its way down, potentially to the leaf node. Insert does the opposite, because we insert at the bottom, so it traces its way potentially up to the root node. So that's a height steps. And heaps have between 2 to the h-1 nodes in them, or 2 to the h-1 entries. And so that's a full heap, or a heap that's just got one entry on the h height. So what does that mean? Basically, the performance is going height steps out of those n entries. So insert and remove are a log n operation, big O log n. Fairly efficient, because we're only going down one side of the branch at any one step. So inserting into a heap is reasonably efficient, much more efficient than if we were trying to insert it into a sorted array, which was log of n, because we had to find the right place. So, a big O of n. So it's a heap is fairly efficient data structure for keeping items in a sorted order. So what is a priority queue? That's the next data structure we're talking about? Well, when we talked about queues, they're first in, first out. Well, that's not always efficient for certain kinds of things. For example, a print queue, you may want to have shorter documents printed before long ones, because then you're just waiting a long time for those long, slow print jobs. So we want to position or put you into the queue determined by your priority. So the first class customers go first, and the second class customers go second. So if a first class customer arrives to a priority queue, they get moved to the front of the queue. So each insertion can reorder that queue. So if a higher priority person or thing comes into the queue, they get shifted up into the queue to their right position based upon their priority. The highest or lowest priority, which is at the front, we remove them depending on if we have a min priority or a max priority queue. So if you want to provide highest priority, the highest priority people are up front, or lowest, depends on your definition of what is good priority. Priority queues are not FIFO. You can get inserted into the queue, a priority queue, and have someone with a higher priority cut in front of you. So they're not traditional regular queues, which are first in, first out. Everybody's treated the same. But they are very powerful and useful data structure for computer science, especially scheduling algorithms where you want the high priority jobs to run before the low priority jobs. So you would want priority queues. So how would we implement a priority queue? Just quickly, I'll go through the code. What we're going to do, or first off, here are the methods on the priority queue. Very much the same as a queue. You can offer, which is add an item to the queue, but it will insert it into the right place into the queue. Remove removes the smallest if you're doing small priority, if you have a min heap to implement this, or it removes the person at the top of the queue or at top of the heap. Poll removes the person at the top of the heap. Peek shows you who's at the top of the heap, and element shows you who's at the top of the heap also. So how are we going to implement our priority queue? Well, we're going to use a heap as our data structure to hold the items in the queue. So we have an array list data, which is our heap. As I showed previously in the slide, we can insert the items into this array list and keep it a heap. And so when we construct our priority queue, we just create the array list. And by using an array lists automatically grow and shrink, so we don't have to worry about array copy and all that stuff that is handled by the Java class, which is very nice. So how do we add something to the priority queue? Well, we use the insertion algorithm that we talked about earlier, where we add the item to the end of the array, which will be the last item into the heap. We calculate the parent or the child and the parent, because we know that the child, because we just put it at the last item in the array, so child is data size -1. The parent is child -1 div 2. And then we do the reheaping algorithm, which is if we're not at the top of the heap, and our last item in is greater than, the last item in child is greater than or less than parent, we do the swap, recalculate child and recalculate parent. We keep doing that until we no longer swap the last item in. It will be in the right place in the heap, and then we can return true. So this is very simple. We do the insertion at the end. We then traverse up the heap, swapping them until it's in its right place. We've solved the problem, and we've maintained the heap. So the other add method that is on a queue does exactly the same thing. So how do we remove something from the head of the queue? Well, if the queue is empty, we return null. Else, we remember the root value, because we're going to return it at the very end. And then this if statement is basically saying if our heap is size 1, then we don't have to do any of the reheaping because we're removing the only thing in the heap. So we remove the thing from the heap and we return. So if there was only one item in the heap, we just remove it from the heap and we're done. Else we're going to do the swapping of the last item in the heap to the first, and that you see that sort of commented out. But so we move the last item in the heap, which is data remove, data size -1, which that's the last item in the heap. We call remove. Remove removes it from the array and returns the value that was removed, and then we set the root to be that value. So we've removed it from the array and we've set the root's value to be that value. So that's a nice line right there that does a lot of work. We set our parent to 0. So now we do the while true to reheap our heap. We know what we calculate the left child. If the left child's out of bounds, it's beyond the end of the array, we break because we're done. We've gotten down to a leaf node and it has no children, so we're done. We've traversed down. We calculate the right child, which is just left child plus 1, and then we're trying to calculate what the min child is. So we first assign it to left, and then we check to see if the right child is less than the left child. If it is, then we change min child, or it was correct in the first place. Now, if the min child is less than the parent, the item that was moved to the root, or moved up, we then swap, change parent to min child, and if we didn't do the swap, we break out of the loop. Else we go back to the top of the loop, recalculate left, break if left is too large, recalculate min, keep going until we find that we don't do a swap, or we get to the leaf, and then at the bottom we return result. So we go back to the item that we remembered here. We remembered the original root, and at the end we return it. So we didn't forget that root that got swapped out. So in brief summary of heaps and priority queues, heaps are an efficient way of keeping items sorted by some sort of comparison by priority, and they provide a very nice way, reasonably efficient way for implementing a priority queue, because the reheaping algorithm is basically a big O of log n, because you only traverse at most from the root to a leaf, or leaf to a root, which is going to be the log n operation. So thank you for paying attention.